Welcome to Module 10, the last module. Woohoo! So in this module, we focus on analysis of categorical data, and that can be represented into different categories. So just a quick overview. Categorical data consists of names or labels or categories. So for example, the gender would be a category because we cannot put a number to it. And even if we have numbers, the numbers don't necessarily represent much in the number sense. For example, the shirt numbers on the professional athletes' uniforms, the numbers themselves don't mean much except they're a substitute for the name. So they're more like categories instead of numerical value. So when you see those types of questions, they deal with the categorical data. So the hypothesis test is observed counts agree with the sum claim distribution. So we have two types of analysis we can do. One is called a goodness of fit test, which is used to test the hypothesis of one observed frequency distribution. The other one is contingency table or two-way frequency table. So we use this when we have more than two or more categories to analyze. In either case, we will be using the chi-square distribution. So let's look at some of the notation for goodness of fit. We're going to be using O, E, K, and N. And for the contingency tables, we have the same thing for O and E, but we'll have R and C. R for rows, C for columns. So let's look at the goodness of fit test example. Say a random sample of about 100 weights of Californians is obtained, and the last digit of those weights are summarized in the table below, which I'll scroll down to a little bit. When obtaining the weights, it is extremely important to actually measure the weights rather than ask people to self-report them. You see the reason why in a minute. By analyzing the last digit, we can verify whether the weights were actually measured, since the reported weights tend to be rounded to something ending with a 0 or 5. So if that's the case, we know the observation was from self-reported weights rather than actually weighing people. So step 1, the original claim is that the digits do not occur with the same frequency. So if I write that in terms of probabilities, it means at least one of the probabilities, P0 from P0, P1, or anywhere between to P9, is different from others. The original, if that claim is false in step 2, then we are saying all probabilities are the same. So P0 equal to P1 all the way down to P9. So all the probabilities are the same. So the writing the hypothesis, we can say null hypothesis is that all the probabilities are the same. Alternative is at least one of them is different. So since we don't have the significance level, we're going to use 0.05 as alpha, and we'll use the chi-square distribution. So here's the table. There are 10 digits, 0 through 9, and O stands for observed frequencies. So we saw that there are 46 zeros, 1 ones, 2 of the 2s, all the way down to 3 of 9s. So you'll be given this table when you're studying the problem. Your task is to do these 4 columns here. So expected frequency, that's easy to tell because in this case there are 100 weights. So if they're equally likely, then each digit will be 10 frequencies each. So that's how I got the 10. So O minus E, basically the difference between O and then E. So in this case, 46 minus 10, that's 36. In this column, what you want to do is square that number we just calculated. So in this case, O minus E squared, that means 36 squared. And the last column, you want to divide that last column by the E, expected frequency. So this, in this case, 1296 divided by 10. You do that for every single cell. And at the end, you follow the chi-square test statistic formula, which is O minus E, square that, sum it all up, and divide it by E. So this cell reproduces this formula right here. This E-looking sign, that means sum, so we're adding it all up. So to do so, we use the function called the sum, and I'm summing all these numbers here. So the test statistics in this case is 212.8. Confidence level will be 0.9. Degree of freedom will be 9 because it's 10 minus 1. So using those two numbers, we can calculate the critical value. Since the goodness of fit test hypothesis test is always right-tailed, we're going to use chi-square inverse right-tail function. So critical value is about 16.9, and p-value using the test statistic here, we get this number right here. If you ever see a E and a negative number, so in this case E and then negative 41, this is a scientific notation, meaning the number p-value is extremely small, very, very small numbers. 0 and then 40 zeros followed by 0 point, and then followed by 40 zeros and then 6825. So it's extremely small number. As you can imagine, because the p-value is so small, we're going to reject the null hypothesis. And also, looking at the critical value and then test statistic, the test statistic falls in the rejection region. So also, from that perspective, we also reject the null hypothesis. So what the conclusion is that we conclude there is sufficient evidence to support the claim that the last digits do not occur with the same relative frequency, meaning we have evidence that the weights were self-reported rather than actually measured, and so the subjects were not actually weighted. So if I were the supervisor for this observation, I have to say go redo these observations. So that's how you do goodness of fit test. Moving on to contingency tables. Here's an example. Below is a contingency table summarizing the results of fit procedures as a success or failure based on different treatments. So you have surgery, cast for 6 weeks, and cast for less than 6 weeks. Here's a success number, failure number. So this is the table I was given to me. So the question is, does it appear that choice of the treatment affects the success of the treatment for the foot procedures? So does it matter which procedure you pick? Do you have a better chance of success, or no, it doesn't really matter which procedure you use? Let's figure that out. Using a 0.05 level significance to test the claim that the success is independent of the treatment group. Okay. Here's a quick requirement check. We see that the test results, test subjects were randomly selected and then randomly assigned to different treatment groups. The results were expressed in frequency counts. These are frequency counts, which is basically count how many success surgeries. And expected frequencies are all over 5. So looking at the success, that's what we're looking at. They're all over 5. So that's good. So all the requirements are satisfied. So let's set up the hypothesis. Success is independent of treatment. Alternative is success and the treatment are dependent somehow. So here's the work you need to do to get to the decision. The light blue part is the numbers you're given. First thing you have to do is figure out the row columns or column totals here and then here using the sum function. And then you also need the row totals, again using the sum function. And you need a grand total number, so you can sum up either columns or the rows. So in this case, it's 253. So we want to get to the test statistic. And again, it's a summation of O minus C squared divided by E. The tricky part with the contingency table is that you have to do this calculation for every single cell differently, separately. So for example, the single E formula is row total multiplied by the column total divided by the grand total. So the grand total part doesn't change, but for each cell, the row total or column total changes. So for here, E of S, that's expected number for success, will be row total multiplied by column total. So the row total will be 66 multiplied by 182 column total divided by 253. So if you look at my references, you see that I'm multiplying 66, 182 divided by 253. So you have to do that for every single cell. In this case, the row total will be 92, column total will be 182 divided by 253. So you do that for every single one. It's a pain, but that's what you gotta do. Okay. And then when you get to here, again, you follow the formula. Take the difference between O and E square and then divide it by E. So for this column, this is the column for success. So I'm going to do is O minus E, which will be 54 minus 47.47 here, square it, and then divide it by, again, this number right here. So that's what I'm doing here. 54 minus 47.47 parentheses, square it, and divide it by 47.478. And again, I had to do that for every single cell. Okay. That's the hardest part, to make sure you're referencing the right cells. When you do so, what you want to do is do this summation part, meaning add up all these numbers here. So I do that in this cell right here. Again, equal sign, sum, and then select all these cells. Close parentheses, press enter, you get this. So this cell represents this entire string of calculations. So that's my test statistic. Let's figure out the critical value. So the R stands for row, C stands for column. So you can see that there are 4 rows and 2 columns. The degree of freedom is, the formula is R minus 1 times C minus 1. So that's going to be 3 times 1, which is 3. Using the test statistic and the degree of freedom, and again, it's a chi-square distribution right tail formula, then I get the p-value, which has the e of -12, meaning that it's an extremely small number. Okay, so we know what the conclusion is going to be, but let's look at the critical value. So confidence level is going to be 0.9. And then using the chi-square inverse function, we get the critical value to be 7.8. So comparing the critical value and then test statistic, you see that the test statistic is in the critical region or the rejection region. So either way, p-value method or critical value method, we're going to reject the null hypothesis. Okay. So what does that mean? Well, it appears that the success is dependent on the treatment. So although the test does not tell us which treatment is the best, we can see the success rate of 81.8%, 44.6%, 95.9%, and then 77.3%, which suggests that the best treatment is to use the non-weight bearing cast for 6 weeks. So how did I get those numbers? Well, that's what I have up here. Basically, it's going to be 54 divided by total number of these two numbers. So that's how you calculate the success rate. 54 divided by summation of 54 and 12. And I did that for every single category. And then you see that here's highlighted darker blue, 95.89%, which is the non-weight bearing cast for 6 weeks. And that seems to be the best treatment if you break your foot. So that's how you do contingency tables. And that's all for Module 10.